Hello and welcome back to Calculus 1 section 3.6, Derivatives as Rate of Change. It has been 2 minutes since we did the previous section, right? The same glorious Saturday. So now we get to put this in a context of application, right? The physical reality, define some words, see how this stuff is used. A lot of application. Clearly, all of physics and engineering rests on this, depends on this. We're going to see some business applications as well, how to analyze certain situations to make the business profitable in terms of supply, demand, production, and so on. First, we have to take a look at two concepts that we covered before. One is the slope of the secant line, which was simply f of x minus f of a, x minus a. You can do y2 minus y1 over x2 minus x1 if that's something that makes you happy, makes you smile. And then we also had m tangent underneath, right? We write m tangent, which was the limit of f of x minus f of a over x minus a. And then we use that substitution thing to make it into age and so on. But these were the two first ideas. So now we are going to look at this and we're going to say, in terms of calculus and applications, we actually have the average change and the average change is going to be f of x2 minus f of x1 divided by x2 minus x1. This is literally y2 minus y1 over x2 minus x1. And then we also have the instantaneous change, which is your derivative. And that one is the limit of x2 going to x1 of f of x2 minus f of x1 divided by x2 minus x1. So we are not learning anything new in terms of mathematics here. We are just tying it to, the vocabulary and then the physical ramifications of what we learn. So to understand the difference between the average and instantaneous, it's easy to use velocity and speed. Even though you're freaking out now, just pay attention and you will understand it. If you go from point A to point B, which is 60 miles away, and it takes you 1 hour, you are using the average calculation in this case, and you will say that your velocity is 60 miles covered in 1 hour, 60 miles per hour. So it took you 1 hour to cover 60 miles. But in reality, did your trip begin at 60 miles per hour? Literally, your car is passing by your house, 60 miles per hour, you're jumping in. Imagine that, right? And forget about the stop signs and the red lights and the school buses, just doesn't matter, right? It's 60 miles per hour until you reach your destination. It's not, right? The car is hopefully parked when you get into it, which is 0 miles per hour, right? And then you might consider to stop for the things that I listed, right? So, well, the law says you should. So looking at this, how to get the average of 60? Well, technically, what averages at 60 if you had 0 at one point? Right? 120, right? And then you say, wow, to counter my 0, I have to drive 120. Yeah, but if you were at 0 for, a minute, then you have to be 120 at 1 minute, so that the average is 60 for that 1 minute. But then you can also be at 0 for a minute and then at 80 for a longer period of time, so that it averages back to 60 again. You see that? Now, we can actually do calculation here to show that speeding actually doesn't save you much time. There is absolutely no benefit of speeding if you are going to school or work, if you're running late. Not just because you can get a ticket. Yes, sure, you can. Double speed zone, $400 ticket and points, and then maybe death, I don't know. The trick is that you literally save seconds. And there is no way that you can save 2 minutes of your travel time by going 80. And you can do these calculations on your own to see. Sure, if your school is in, Boston, and you're going from New Jersey, yes, you can save 5 minutes by speeding, sure. But from the distance that you travel here, you actually can't. And risking crazy driving and tickets and all of that kind of stuff is not worth it. And you can actually use these calculations to check that on your own. So what is the average speed? Average speed or average velocity. A difference between speed and velocity is that velocity also gives you the direction, right? So they say speed limit on the highway because they hope that you have that common sense that you will go with the traffic, you know what I mean? The same direction. So on 78, it doesn't say velocity, a limit 65 miles per hour forward, right? Yeah, I know. One day those signs will not exist. The cars will be autonomous cars, and you just sit and where would you like to go, sir? Yes. Wake up and you're there. Widescreen movie on this windshield in front.
They have prototype drones right now, where it's like it has certain locations that you can go to and you put the button into.
Yep. So drops you off in front of the school, goes park somewhere. You don't even know where it is, because you'll call it. Just say, pick me up.
You won't actually even own the car.
You don't even need that, yeah.
Cars are efficient. 99% of the time it's sitting there in a driveway or parking lot.
Exactly. So, and you still pay $30,000 for them. Everything works just fine. So, the only time when you are really in a rush is if you really have to rob a bank and you just have to, that's when you really need a car. Other times you can just plan and wait for like 2 minutes. It's okay.
That's one bad thing about self-driving cars. Any recreational use, like any off-roading or anything like that, any pleasure driving, is going to spike way up in price.
Yeah.
Just because they won't make recreational cars on that scale anymore.
No, you can have a regular car that we have now, which would be exotic car at that point.
Once self-driving cars are the norm, due to the fact that they're going to be making relatively few driving cars, due to economy of scale, they're going to increase in price for it worth the company to actually produce the car.
Exactly. So it would switch the price, and insurance companies will make that switch like this, so we have no issues. Autonomous cars will be a reality very quickly, which is awesome.
People think it's not going to be legislation that'll force out people driving. It'll be insurance.
Insurance, yep.
Due to the fact that it costs $1 to insure a self-driving car, goes to a self-driving car company will cover most of it, and it'll cost infinitely more to cover a human.
Yep, because cars don't get stupid while driving.
They won't make a mistake, and if they do,
What happened?
What if you have a perfect human? There is
Perfect human? There is no perfect human. There's no perfect autonomous car either, but they're better. So insurance is going to say $5 for $5 a month if you have autonomous car, and then I don't know, $5,000 if you have the dumb car. Yeah.
won't even be liable for the person. It'll be the programmer.
I'll pay them 500,000.
That's okay. All right. So guys, we understand hopefully the average velocity. So the average velocity, if you have the velocity bar, you start at 0 velocity, then you speed up to, I don't know, 35 miles per hour, residential, you drive at 35, then you go up to 55, then you have a red light, you have to stop, then you again speed up to 55, then you stop on the next red light. This is you're driving on 22, then you again speed up and you drive and so on. So this is how a velocity graph would look like for all velocities, right, that say, okay, there is a driving time in a residential area, then you get onto 22 highway, you are driving at 55, then you red light, then drive, then red light, then drive. And the average one would be, you know, somewhere in here, right? So that would be the average line. Now, what is the instantaneous velocity, the actual, the derivative? It is your speedometer. So as you are looking at the speedometer, speedometer is showing the velocity. It's showing that current, the instant velocity that you have. So as soon as you see a cop on the side of the road or behind you, right, you immediately glance, right, at the speed, right? It's that oh crap moment, right, that you have, that instant moment. That's the derivative, right? So you don't get the, what do you do? The ticket is written for that instantaneous speedometer read. And the difference between the instantaneous and the average is this. You can think of it as a difference between a photograph and a video. The average would be taking a video over a long period of time and you just see what happened. The photo is this one snapshot in time, which is infinitely small, right? The shutter goes fraction of a second, like, and that's it. So that particular instant in time is captured and you see someone's change, right? Someone was jumping or someone was doing something, right? There was some kind of change and was captured in that instant. So that's the derivative part. And when you watch the movie of someone jump and then land, that would be the average because you are looking over the long period of time. Also, the photo finish for races and so on. There are a lot of different ways that you can understand the difference between the average and the instantaneous. So if you get a formula for any type of path, for instance, if I give you, right, take a look at that, right? That was the negative x squared parabola, right? So in physics, you learn the formula that says that the height is negative 1/2 gt squared plus v0t plus y0. You learn this formula in physics. It's actually derived through differential equations in mathematics, and you will actually see this derived in class in Calc 2 and then again in differential equations. This formula has all of the features of this particular path. So let's take a look one more time. Now observe. Is it going to be the same if I throw it from here or from here? Clearly not, right? This one should go further. Well, that's this part of the equation, right? That's this part of the equation, which is initial height from which you throw the object. Then we also have a throw where I, use more force to throw it than if I do the kind of part and just goes right down. Now that one is here, V0, initial velocity, how hard you throw. And then obviously you have the gravity term, which is the one that actually right? Make sure that the object goes down. So when you look at this particular motion, only from the y perspective, the object will go up, it will stop, right? Because the gravity is the one that slowed it down. As I throw it up and then catch it, the object was, when I throw it, it was constantly slowing down by that gravity term until it stopped at the peak. And then the gravity pulls on it down. It doesn't pull, but all right. So it went down and it changed the direction of velocity. So all three terms are important, right? This is due to the gravity of the Earth. This is how hard you throw. This is from which height you throw. And all three work together. So now, when you look at this equation, you can find velocity as the derivative in respect to time, because you know that change in distance over change in time is the velocity. And as soon as you do this, the t squared, right, 2 goes down, kills the half. You have negative gt plus v0. Those of you who took the physics courses, you already know that velocity final is velocity initial plus acceleration times time. That's that formula, except with gravity, negative, right, pulling down, so we have negative g, but that's the acceleration. So you see how all of these things make sense. And if you take one more derivative of this to get the acceleration, you see that acceleration is negative g, right, which is downwards, negative, and the gravity. So all of these formulas make sense. So now when you have these two formulas, I'm going to erase the physics iteration of it. When you have these two formulas, if I ask you how high is the object in 3 seconds, that's 3, and you compute. If I ask you, and do you have this? Sure, this is 9.81, and it was 3 meters per second squared initial throw, and I throw it from 3 meters tall, right? That's given. How fast is it going at 6 seconds? With this formula, you put 6 there. So it's very easy to trace the objects, and that's why you can program, autonomous cars and other things, because you can do this, right? It's equations. These equations work, and all you need to do is to program it and make it work with the hardware. So say we throw object from 1.5 meters at 3 meters per second. Find position equation, position and velocity equations, position and velocity equations. So that's part A. Part B, what's the max height? Part C, position and the velocity after, I don't know, or at, let's do at t equals 4 seconds. So these are all questions that we can find. So we immediately know that the position function for this parabolic motion is going to be, you know what, just for sake of laziness, g equals 10 meters per second. We know it's 9.81, but then, calculator and yeah. So it's going to be negative 5t squared plus 3t. Who choose 1.5? Whatever. There you go. So that's the position function, right? I have negative half gt squared. Well, if g is 10, half of that's 5, so negative 5t squared. v0 is 3, initial velocity. So now all I have to do is plug all of these things in the equation, and I have the equation for position. Take the derivative for velocity, dy dt, and we have negative 10t plus 3. So this is answering your part A. And I can immediately answer part C just by plugging in 4 everywhere. So y of 4 is is what? What's y of 4? I have 20, 80, negative 80, plus 12 is 68, right? Negative 68, negative 66 and a 5 meters. And velocity at 4 seconds is going to be negative 37, thank you, meters per second. Now all these negatives make sense if you think of the direction forward and backwards, and in terms of the displacement above x-axis or below x-axis. So it's just a locational coordinate system. What's the max height? That's usually the trickiest one. Well, the max height happens at velocity is 0. Remember, the graph looks like this, and here is when the slope is equal to 0, which is velocity is equal to 0. And that's the max height right there. So velocity equals 0 means negative 10t plus 3 equals to 0. And that's 3/10, right? So t equals 3 over 10 seconds. So it's going to get its maximum velocity, sorry, its maximum height at t equals to 3. So now you just do for y max, you need to find y computed at 3 over 10, which is negative 5, 3 over 10 squared, plus 3 over 10 times 3, plus 1.5, and that's going to be a number, right? So 9 negative 45 over 100 plus 90 over 100 plus 150 over 100. That's 45, 195 over 100. So 1.95 meters is the maximum height. Easy. So you can do a lot of cool stuff with this. You get the path for the particle. Doesn't have to be parabolic. You can put to go on e to the t curve, sine t curve. It doesn't matter what the function is. Function will describe the path. And then of the particle, you take the derivative of that path to get instantaneous velocities. Now, how do you get the average? The average will have to give you 2 points between which you are computing it. So say that particle travels on y of t equals to, I don't know, 3 square root, oh, can't do that very well. Oh, I can. I'll just do the vanilla one. Plus t minus 1. So that's the path that the particle is taking. It's going to be some kind of curve. And we want to know average velocity from t equals 0 when it starts to t equals, let's say, 3 seconds when it ends the journey. So that's all I want to know. All right, cool. So average is going to be f of t2 minus f of t1 divided by t2 minus t1. So it's the final stage minus the initial beginning stage. So I will have f computed at 3 minus f computed at 0 divided by 3 minus 0. Now plug these values in. Plug in 3. Who picked 3? 3 root 3 plus 3 minus 1 minus 0 minus 0 minus 1 divided by 3. Oh, these will cancel. Nice. So I get 3 root 3 plus 3 over 3, which is root 3 plus 1. You factor out 3 and cancel. So root 3 plus 1 is the average. That's the average velocity in this case. I have the position function given by the whatever crazy function you get. As long as you are able to compute, you're good to go. So it could be e's, could be ln's, could be sine x, cosine x, could be combination of all of them. It doesn't really matter. Plug these values in and you get the answer. We can also ask for instantaneous. You will have to first find the derivative. So y prime of t, which is the velocity, would be 3 over 2 root t. I hope you memorized already that the derivative of root x is 1 over root 2x. I told you that last time. Plus 1. Derivative of t is 1, and derivative of negative 1 is 0. So now, what's the speed at, what's the velocity at 3 seconds? It will be 3 over 2 root 3 plus 1, which is 3 root 3 over 6 plus 1. That's exact already. Now, if you really want, this is 1.72, so if you call that a 2, then it's roughly canceling, so I don't know, 1.94, whatever. What is it? Punch it, Brian. Yeah. 1.87. Yeah, I'm bad. For some students said, oh, wait, so if I'm looking for average, do algebra, and if I'm looking for instantaneous, do calculus. Sure, okay, go ahead. Yeah, that's it. Instantaneous is the derivative, and average is your algebra calculation. Slope, y2 minus y1 over x2 minus x1. So we got that. Business. So if we are talking about business applications, we have, so economics and business, they like to make up their own words, so we have to learn the words now. For whatever reason, derivative is now marginal. I don't know why, but it's called marginal cost, marginal revenue, marginal profit. Let's just take the derivative. That's all it is. So you got to learn vocabulary. Other than that, calculations are the same. You have averages, you have instantaneous. So you'll have average cost. And you average cost over time, because it's easy to think that way. You have to understand that setting up a production costs a lot of money. Why is Tesla S so expensive? Well, A, it's the only American-made car in America. That's it. Not Ford, not GM. They don't have their facilities in the United States. Tesla is the only American car manufacturer. Manufactures all of the parts, does all of the engineering and all of the production on American soil. So it's the only company in the United States that you can say it's American car. Everything else, Ford and everyone else, they have their facilities in Mexico and offshore, They import the cars to be sold here and Europe and elsewhere. So why is Tesla so expensive? It's a revolutionary technology. Nothing like it exists on the market. They have to invent the factory that is going to make the car they invented, all right? So setting up production like that costs a lot of money because you have to make the machines that will make everything on that car. So we are talking insanely high initial cost because you don't get to recycle last year's model because last year didn't exist, right? Well, when they started the production, obviously. So they don't get to modify existing robots or anything like that. They have to do everything from scratch. Make the building, put the machines there, make the machines, right? Program the machines, and then hire people, train the people, and all of that kind of stuff. You know, very few people work there, actually, because if you haven't seen Tesla factories, and it's on YouTube, it is just amazing. And guys, those are your jobs. Your jobs are not in manufacturing in the future. You have to make the machines that will make stuff. They have robots in that factory that change tools. So it's one robot that it's doing a lot of different stuff. It's not an assembly line in the sense that regular car manufacturers where you have a robot that will weld along one side and then production moves and then it welds the same thing. One robot does the same thing the whole day. It's not that. This is the thing that does the whole block. It changes the tool. It does things. So it's a lot of a lot of programming and a lot of just watch that stuff on YouTube. It's really impressive. So setting up the cost of initial is really high. So when you make just one of something, right? You make one unit, then that unit is not just the cost of materials, it's also the cost of setting up the factory and setting up everything. So the first Tesla car that is ever made had to be, what, $1 billion, let's say, right? You can't sell it for $1 billion. Well, obviously Bill Gates can just write a check, but some people can. But what you do is, as you make, if you make 2 cars, cool, now that $1 billion is 500 million each, right? And when you make 10 cars, then it's 100 million each, and so on, right? So the initial cost of setting up the factory has to be included in the price of the production, not just materials and so on. That's why I'm so annoyed when clothing is like, a piece of cloth is $300. Like, what the hell? There's no robot that is manufactured that is state-of-the-art technology that has to weld and say you have some poor kid in Malaysia that is sewing for like a meal, right? And it's still charged $300. It's just insane. That's true. Don't look at me that way. We all know what we wear, and we still wear it. The tears keep you warm. That is the new level of evil. That's the new level of evil. I was trying to be as sarcastic as I can possibly be, as poisonous, but you just took it to a new level. So yeah, I'll try to incorporate that next time I teach this section. Yeah, I know. So yeah, that's what I'm going to ask for next time when I'm at a restaurant. Like, what would you like to drink, sir? A cup of children tears. On the rocks.
And the rocks are blood diamonds.
There you go. Wow. All right, this is getting worse, so let's go back into business, which is actually not going to make it better at all, because that's all it is. The business rests on, I guess, extorting children work in mines and in the sewing machine. All right. So average and marginal cost. Average and marginal cost, we are going to have the fixed cost. Fixed cost is going to be setting about the production. Fixed cost is also materials used, right? So we have the just want to see if they actually define this in one box. Yes. So the cost function will have the average cost is equal to the cost function divided by the number. So cost function divided by the number of units produced. So that's the average cost. But as I said, the cost of the first unit is not going to be the same as the cost of the 100th unit. Because if you only produce one of something, that unit has to take into its cost to absorb the cost of facilities, cost of development, cost of everything. When if you have 100 units produced, that kind of cost is spread over 100 units. So the price of each individual unit obviously goes down. Marginal cost is the derivative of the cost function. So this is what you guys are learning, okay? That's the formulas. And now we're going to put this, discuss the problem. And I'm going to use the one that is done in the book because it's very easy to follow and understand. And then I believe they have 2 or 3 for you to practice on homework. If you have any questions, obviously you will ask next class. So what do they have? They have a cost function for producing X units that is negative 0.02 X squared plus 50 X plus 100 if they are producing between 0 and 1,000 units. Now, this limit up to 1,000 units might be because, I don't know, machines are good up to 1,000 units and then you have to change them or whatever. So up to 1,000 units, this function is the best fit for the cost. And now we can do the analysis of the entire cost to see how much the cost is so you can price your product well. Usually they say the markup should be, 60%? Yeah, depending on the product, yeah. Yeah. So you kind of have to make sure that you're doing this right, because if you price your product less than the cost, right? A lot of people don't understand when you run the business, you actually have the cost of gas and transportation, right? And electricity and phone lines and, salaries. It's all cost. It's not that, oh, I need to bring in, $3 per pound for plastic and then, make something and sell it for 6 cents. Makes no sense. All right, so what do I want to know? Determine the average and marginal cost functions. So what's the average function? The average function will be the cost function divided by x, which is the number of units produced. So we have negative 0.02x plus 50 plus 100 over x. So that would be the average cost. And the marginal cost is the derivative. So we have negative 0.04x plus 50. So these two, this is the average cost and this is the marginal cost. And now we want to take a look at, so that's part A, we want to take a look at determine the average and marginal cost for the first 100 units. So what's happening for x equals 100? Well, we plug that in, right? You plug in both of these. So the average cost for 100 units is going to be negative 2 plus 50 plus 1, which in my book is 49. 49 what? Currency. Dollars per unit. the number of units produced. So you see the cost is in money, right? It costs you $10, costs you $100,000, right? And then you're dividing that by units. So the answer has to be cost, right? Money per unit. So if you're talking dollars, it's dollars per unit, or yen, right? Or rupees. Now marginal cost at 100, we compute the same thing. We get negative, so that's negative 4 plus 50. And we get $46 per unit. So we now have two numbers for the same input of 100, have two different numbers. And I want to compute immediately the second part, which is for 900, I believe. Yep, for 900. And then we're going to discuss the differences between this. So x equals 900. The average one for 900 is going to be what? Negative 2. So 900, that kills us, that's 18. 9 plus 50 plus 100 over 900, that's 1 over 9. 1 over 9, that's 0.11111 forever, right? So it's something is wrong here. Oh, it's negative 18. Negative 18. So I have negative 18 and 50, that will be 32. 11111, right? We keep two decimals because it's cents. Dollars per unit. And now we do C prime at 900. That's negative 4 times 9, negative 36. Plus 50 gives me $14 per unit. Awesome. So what do we learn from this particular calculation? We look at the production here. We see that if we make 100 units, the average cost for producing these 100 units is $49 per piece. So that's like iPhone production right there. That's how much it costs. Chunk. And then they actually are able to market and sell it because they're able to trick people. So you have a $49 per unit to make on average. Now $46 is the cost of the 100th unit produced. You see, if you are to compute this for 2 units, this number will be much higher, right? Because that will be, what's the cost of producing the second unit? So this is producing the 100th unit. Remember the derivative is that snap in time? So what's your velocity at 3 seconds, right? And the average is what is the velocity over 3 seconds. So this is that over, right, long period. So this is averaging all 100 units, but this is the unit. 100 unit cost you $46 to make. 900 unit cost you only $14 to make. So this model predicts that the more you make, the less cost you have in terms of production. And you can see that, right? You see that even the average one falls down in a production. So why is that so? Remember, you set up factory only once. Yeah, sure, you have to maintain it. But you set up factory only once. So you spend, I don't know, $150 million to set up a production. And you make the one product. Well, it's 150 million plus whatever else you have for that product. But if you make 150 million things, right, that's 10 cents per each, right? So you have to understand how this works. The marginal cost is the cost of the unit. you are observing. So I observed the 900 unit produced, and it cost me only 14 bucks to make it. I observed 100 unit, and it cost me 46 bucks to make it. You can actually just look into the equation and see how much it costs you to make the first unit. Well, to make no units, what's the cost to set up the production? 100 bucks, right? Because if I'm making no units, that's not there, that's not there, it's just this term. Whatever this function is, whatever it's made over here, it costs 100 bucks to set up the production, and then the rest is cost. Now you see that as soon as you make 100 units, that initial cost of 100 is now 49 for all of the, right? So if you make 1 unit, how much is 1 unit worth? Well, you see that? It's 149 cents. 149 and 96. That's what it is when you compute it there. No, 98, sorry. So this is how the cost is done. And guys, this is actually real stuff. You know, Sanofi and Johnson & Johnson and these huge companies, they actually do this, and these are your jobs. This kind of analysis, the average cost and marginal cost, because it's not when you have your small home bakery and you make 10 donuts and then you sell those 10 donuts and you're good for a day. No, these companies move billions of dollars. And when you make a mistake there, it's $100 million mistake. So it's a high stake jobs in this kind of business thing. And you have to know a lot of math to actually hold those kind of jobs. And then talk about Wall Street and so on. There are layers to business. And obviously calculus brings certain level to that. That's it. There's also this one part that talks about elasticity in economics. Again, it's too specific for calculus class. It's again just the derivative. You get the function, take the derivative. If you're interested in that kind of stuff, read that part. And yep, that's it. That's it for 3.6. Let's go have a break. One more section afterwards.